In this section, we'll look at the area between curves. We started in Chapter 4 when we worked with integration, finding the area under a curve. So it shouldn't be a big surprise to see that the area between two curves is going to be the difference between those two integrals, or the integral of the difference of the two curves. Here's an example that makes this a little bit more concrete. If you look at two constant functions, let's just call those constant functions f of x equals 7 and g of x equals 3. If we found the area under the pink curve, that's this part that you could see had pink lines drawn through it, we'd get this rectangle whose width was b minus a and whose height was 7 units. Or in other words, it's the integration from a to b of f of x. And then when we look at the blue function, the g of x function, let's call that a sub 3. The area of that rectangle would be the difference between a and b, so the width, b minus a, times the height, 3. Or we could see it as the integral of g of x from x equals a to x equals b. So if we highlighted that blue, we could see that the part that we're looking for, the area between the pink and blue, could be described as area sub 7 minus area sub 3, or 4 times the width, 4 times b minus a. You can see that that is the same as the integration from x equals a to b of f of x minus the blue integration from x equals a to x equals b of g of x. So we can see this formula become a little bit more clear with a constant function. It will be helpful to note that when you have a function that represents a velocity of an object's displacement, the area under the velocity curve a from x equals 0 to x equals t seconds represents the distance traveled by the object in t seconds. So the area between the two velocity curves represents the distance between the two objects at a given time t. So you see that we'll be able to transfer this process for finding the area of a region bounded by two curves to another application, the distance between two objects at a given time. Let's look at another example. Let's look at the example. This is example 2 on your handout sheet if you're using the handout from Blackboard. And in example 2, we want to find the area of the region bounded by y equals x plus 6 and y equals x squared. We're given some hints that we should sketch the region, determine the endpoints, or where the two curves intersect, and then write an integral and find the area. Well, I've graphed the two functions. We've got y equals x plus 6 is the pink line above, and y equals x squared, the blue, that's lying below. And I can find these intersection points by solving a system of equations, y equals x plus 6 and y equals x squared. I used the substitution method. I substituted x plus 6 in for y and got x squared equals x plus 6. Solving this quadratic equation for x, we get that the two endpoints are x negative 2 and x equals positive 3. So we have our two intersection points there. And you could see that what we're looking for now is the area of this yellow region in between the blue and the pink. So to set this up, I'm going to do the integral of the top function, the pink function, minus the integral of the blue function. And so that would give us that part that's in between, or the yellow. It would look like this, and we're going to go from x equals -2 to x equals 3. The way I determined the -2 and the 3 was by finding where the two functions intersected. And that's always, in these types, the first step, because we need to know where we're integrating from and to. So we're going to integrate from x equals -2 to x equals 3 because those are the two x values where the two functions intersect. And we're going to do the pink function, the x plus 6, because that's the upper function, minus the lower function, the parabola lies below the pink line, x squared. And that's it. We could do a review of integration by integrating those. I'm going to start by doing it in descending order. The opposite of x squared plus x plus 6. Then when I integrate that, I'd have the opposite of x cubed over 3 plus x squared over 2 plus 6x over 1. We don't really have to write that one. And since this is a definite integral from x equals -2 to x equals 3, I'll draw the vertical line to show that our two endpoints are -2 and 3. The next part of evaluating a definite integral is going to be to replace the x with 3 and the x with 2 and subtract those two values. When we do the substitution and subtract, we'll get 125 over 6. If you'd like to, you could pause the video and calculate this out yourself to verify that you are in fact able to get the same result. That's the first example, and that's the example 2 on your handout. Find the area of the region bounded above by y equals x plus 6 and below by y equals x squared. Let's go on to example 3. Example 3 asks us in the area of the region between three curves. We've got y equals 1, y equals the opposite of x plus 6, and y equals the square root of x. We're going to start by graphing region, sketching the radical and the two lines, the green line, the blue line, and the pink curve, and finding where they intersect to determine those endpoints of where we're going to integrate. When I did that work, I found that the endpoints were at x equals 1, y equals 1, x equals 4, y equals 2, and x equals 5, y equals 1. I also noticed in this sketch that from x equals 1 to x equals 4, we've got the pink curve, the square root, above the blue curve, the horizontal line. But then from x equals 4 to x equals 5, we've got the green function above the blue function, or the line, the opposite of x, above the line y equals 1. So I'm going to need to break this into two separate problems because we have two separate areas. I'm going to try and display that for you using the same colors as the curves. So you'll see how I've set this up, that we've got that from x equals 1 to 4 of the pink square root of x minus the blue y equals 1 over dx. And we're going to add a little triangle. And by the way, you could use some basic geometry, area equals 1/2 base times height, to verify that your integral gives you the correct value. But we're going to integrate from x equals 4 to x equals the green line, the opposite of x plus 6, minus the blue line, y equals 1, all over dx. When we integrate, and by the way, a tip if you're still working on integrating, we'll write the square root of x as x to the 1/2. When we integrate, we'll have x to the 1/2 plus 2/2, so x to the 3/2 over 3 times 2 minus x, and that's going from x equals 1 to x equals 4. And then with the second area, the triangle, when we integrate that, we have the opposite of x to the 1 plus 1, or 2, over 2. Once and negative 1, I get 5. So integrating 5, we 5x to the 1 over 1. And that's going to go from x equals 4 to x equals 5. At this time, you may want to pause the video to plug in your x's and do the subtraction, do the arithmetic, whether you're doing it by hand or with a calculator, and verify that you're going to get the same result. When I did the calculation, I got the area under the pink curve as 5 over 3, and the area under the green curve as 1 over 2. And then, of course, when we add those, we get a 13 over 6 as the final area, the total area. Please note that you do want to leave this as an improper fraction, not as a mixed number, and not as a decimal approximation. Well, that concludes the examples for the area between two curves. If you have questions about these examples, please bring your questions to class.